see if it's working better. Yeah.
Yeah.
That's just going to wander around every time.
Shouldn't, but yeah.
Okay.
Hi, I'm Indrek from the ESTcube 1 team, and well, this there on the slide is an auto-portrait of ESTcube 1 from the French Guiana Kourou clean room. And well, ESTcube 1 was a one-unit CubeSat developed mainly by students from the University of Tartu, as well as a few students from Tallinn University of Technology and Estonian Aviation Academy. And in the project, we also had foreign students from Latvia, then Ukraine, Germany, and even Finland, and yeah, a lot of help from all around the globe. Then a little bit about the experiment that ESTcube 1 is about to perform, but the software for which is not ready yet completely. Well, ESTcube would be, or ESTcube is at the moment on a polar orbit at an altitude of about 700 kilometers, and for the mission it would start spinning itself around this spin axis, and as it would do so, it would start unreeling the tether and like record the unreeling of the tether along with its end mass to make sure that it's still in one piece. And after that, we would on the polar regions periodically charge the tether to have the satellite accelerate its spin in the flow of ions and electrons and then in the higher atmosphere plasma environment, to see if the electric solar wind sail effect is also measurable on this like sort of simulated environment in the higher Earth atmosphere, as like the next missions would take it further by going beyond Earth magnetic field, and then there we could actually test it with the real solar wind. Yeah, and on the polar areas, then the measurements from gyros for spin rate would be recorded, as well as the tether voltages and currents, and the orbit parameters of ESTcube, because these are also expected to change during the mission. Okay, well, that's not too good, but anyway, so far well, there's a lot we have learned, because we have done a lot of stuff wrong as well, but well, first off, at first we didn't really have a good idea of what the different subsystems should do, and then we had this crazy like idea that we should have it as redundant as possible and as fault tolerant as possible. So we had different subsystems taking over the functionality of others, and stuff became really complex. And there are still remnants of these old ideas in the design. Then we started prototyping and testing integration rather late in the project schedule. Well, because we started off the ESA way, we started producing a lot of documentation first as to how to design it, and then at some point we realized that we would still want to launch the satellite, not a bunch of documentation. Then we we really started rushing things, and yeah, since the satellite was really not designed for assembly and disassembly, then we only had one chance to fully assemble it, and we couldn't fix it anymore if anything had gone wrong there. Well, which actually did. There's one loose wire on one sun sensor, but that's not that big of a problem, luckily. And it's often a good idea to actually design the system as a bit of an overkill. Like at first, we thought that, well, the onboard computer doesn't need to do much actually, and so we thought, like, why not just use an AVR 8-bit controller? But well, then I found these ARMs to be more power efficient, and well, took those. And then later, gradually, the requirements of other subsystems for the onboard computer started increasing rapidly. And now even this Cortex M3, like STM32F1, is like it's not enough for those ADCS Kalman filters and 64-bit floating point arithmetics and stuff. So yeah, and also for simplicity, it's often a good idea to have the system capable of doing more. Like we spent a lot of time actually re-implementing features and stuff that's already there in some Linux-based distributions for embedded systems. But well, we just didn't have the power budget to actually have such a microcontroller there with enough memory to actually run any Linux. So we took FreeRTOS and implemented a lot of code ourselves. And the same for electronics. We really had to design a lot of the electronics by our own because the power requirements were too high for us. And we were lacking technological, or I don't know how it should be called, systems engineers who would kind of look through all the communication lines between the subsystems, like make sure that the UART, RX and TX lines are in the correct order. Or at first they weren't. Quite, like, I guess between the communications and the onboard computer, at least it was wrong at first. And since there was no systems engineer doing that, then it was this EPS guy, Erik, who had to do it. Well, he had to do a lot of stuff that was actually meant for the systems engineers. He worked on the connectors, he worked on assembly, he worked on well, like preparing the glues and all the materials for the assembly, and actually he did a lot of work which was not the work of electrical power system actually. And then we found that I2C has a lot of quirks that need to be taken into account when designing high reliability systems and satellites. And then there's a few notes on it. Well, usually I2C works pretty well when there's just two devices, one master and one slave. There's usually not much to go wrong there, but let's say that there's three devices and one of them is switched off so that it doesn't have any power. As soon as that happens, then this device A can no longer communicate with device C because device B is draining all the signals on the communication lines due to the integrated EST diodes, so that the device B is half powered actually, and it's in I don't know, in some sort of a state where it doesn't work correctly. It does something random, and yeah, messes the bus up as well for I2C. Then there's a solution for that, which is like which also works in the case where this device B would be still powered but wouldn't be working anymore, so that it would have just like blocked the bus for some reason, which actually happened with our gyros pretty often. Well, the solution would be to have the possibility or the ability to switch off different I2C devices separately, and then have switches or muxes to disconnect the communication lines as well. So then if one device happened to stop functioning, then we could just power recycle it while having the connection lines disconnected, so that we could still communicate with the rest of the devices when that happened. And also, one should really triple check the I2C addresses against conflicts, especially when there's multiple subsystems having I2C devices on the same bus, and there needs to be this coordination of I2C addresses. But well, yeah, we had a lot of problems, and so, but we were still lucky, and we have a few results as well. So far it has been more than 1,000 orbits of ESTcube working in the orbit, and we have received beacon recordings and like beacon decodings from around the globe. A lot of thanks to all the radio amateurs who have received the beacon signals. Although, yeah, the beacon transmission from ESTcube has been actually switched off or disabled pretty often to save power for some other tasks or tests or whatever that's going on that the operators are doing. And well, yeah, we don't have a good system for like indicating the state of which the satellite is in. So if the beacon is enabled or disabled currently or not. Yeah, and we have also received about 7 megabytes of packet data, and have sent 3 megabytes of packet data up to the satellite. We have so far been able to upgrade electrical power system firmware for 5 times, and onboard computer firmware twice. Then we have logged some attitude determination and control system parameters and measurements, as well as electrical power system measurements on the onboard computer, and downloaded the files successfully. Then we have gotten quite a few camera images, and yeah, I guess 2 days ago when we visited the SSTL as well as had other tours then in the labs and the rooms there. We had a pass of ESTcube flying over Europe, and then we also received pieces of a new image, which unfortunately is not in this presentation yet, but I was really amazed by this photo actually, because it's nothing like any other photo we have received so far, so I could show it later from the laptop. Anyway, here's one of the images that ESTcube has received. On ESTcube 1, the camera is VGA, is of VGA resolution, and with the current camera software, there's no compression, and yeah, it takes about 4 days to download a full picture, at least. And well, there's another one, and another one, and all these 3 images have been processed actually, so I could maybe also show some of the raw data later. But yeah, there have been a few glitches from radiation effects on the images as well, which due to which the unprocessed images don't look so pretty. But yes, there's some info on the radio. Well, there's data on, or like info on the beacon, which is for most of the time it's turned off at the moment yet. But in the upcoming weeks we'll upload newer firmware after we have finished testing it, which will change the beacon period, or like the time between the beacon transmissions would be varying depending on the power state of the electrical power system, which would allow us to keep beacon on for a longer period of time actually. And also with the upcoming upgrades to the firmware, we will have a packet beacon. Yeah, and the period between the packet beacons transmissions could be even smaller. Yeah. So, does anyone still need to write anything down, or can I switch the slide to the next one? Okay, thanks. Okay, so I would quickly provide a small overview of this Hummingbird and our mission control system software that we're using. Well, Hummingbird is a CGI thing, and it's basically a bunch of building blocks connected with a Patch Camel or ActiveMQ signaling system, and these blocks would contain like packet encoding, decoding, then telemetry, calibration, limit checks, command scheduling, verification, and also scripting, then orbit propagation with the newer Hummingbird version, all sorts of notifications via email or SMS or whatever, and storage of parameters, and yeah, and all this with an open source package with Apache 2 license. And our mission control system is, well, it's basically Hummingbird as the core, with a few modules developed for our ground station, as well as this front end that's still in continuous development. And well, yeah. So I guess that there's one important detail missing from here. It's the custom FSK transmitter that had to be built for our communications system due to an unfortunate choice of the controllers or the chips. So yeah, this TNC module actually communicates with the TNC as well as our custom transmitter. And yeah, otherwise I guess that's about it. If anyone has any questions.
Wow, no breaks in that one. Thank you very much. Has anyone got any questions from the floor first of all? Quinton.
Do you have any?
If you repeat the question on the side.
Do you have any results yet from your mouse tail with the electricity in the high polar regions?
Yeah, because since we don't have the software fully ready yet for the mission, then we haven't started with it because it would be slightly dangerous and we might just lose the satellite. Or at least during the testing or vibration testing, we at first encountered well, a few problems, because in the design of this tether reel and the motor, there were no locks, so the motor started rotating in the vibration environment, and this caused destroyed the tether, so that it became a dust of tiny aluminum fibers. And yeah, well, we got that cleaned up and then added a lock there and tested it in the vibration environment, but we are still not sure if the tether is intact and if everything would work if we really started reeling it out or really started powering it to 500 volts.
That'll be your last experiment.
That will be the last one, yes, after we have...
Okay. Chris?
Yes, when you actually... Thanks for that. So when you actually deploy the tether itself, and apart from obviously collecting large amounts of charge, which is dangerous itself, how does that going to affect your antenna pattern and your transmission and reception up to the spacecraft?
Well, yeah, hopefully it won't coil around the antennas, but...
It'll create a field, won't it?
Yeah, but otherwise, I guess there have been simulations on that, but I can't really say anything about the results, so I can't remember.
I can say a bit. I think there were some simulations, but it was basically the conclusion was that it won't affect that much, so we don't have to worry about it, I think.
Thank you.
Do you have any other questions from the floor before we go? Did you have one earlier? Yeah, it's been answered, is it? Okay, have we got any from the net? Web?
Any questions from the web?
Right, let's show our appreciation. Thank you very much.